All right, so now we have seen how to do leave one out cross-validation and k-fold cross-validation for regression. So what about classification? So for classification, there are basically two possible ways to measure the error of a classification model. So one of them is the more straightforward, is just the overall error rate. So I'll just give you an example. So suppose that we train a binary classification model, say the true labels are yes or no, and the predicted labels are yes or no. And let's say we predicted, so there are true positives, so 100 true positives, 200 true negatives, and probably 50 false negatives, and I don't know, let's say 30 false positives. So in this case, the overall error rate is going to be what? It's going to be the number of misclassified observations divided by the total number of observations. So the number of misclassified observations is 80, and the total number of observations is 380. So this is the overall error rate. So versus the other error function that we used was, recall how we trained the logistic regression. So we trained it by applying the gradient descent to this to this error function that comes from maximizing the likelihood. So, and this is binary cross entropy. So our cross entropy. I'm not going to write it down. It has a complicated formula with logarithms and all, but you probably recall that in order to train it, to train a logistic regression, we use this cross entropy. So to do cross validation, we use overall error rate instead, right? So for training binary models, we do cross entropy, but for cross validating, we do the overall error rate. So there is, I do not know a good theoretical explanation of that, so it's probably just like an empirical fact. I'm not sure. Maybe it is mentioned in the bigger textbook, Elements of Statistical Learning, that is just like for graduate students. In any case, just accept this rule. So here is what I did. So I conducted a numerical experiment again, right? So to generate this data set, so I came up with a true decision boundary. So this true decision boundary is just y is inverse tangent of x. So whatever is above is good, right? So if y is bigger than the inverse tangent of x, is good. If y is smaller, is labeled as bad. And then I switched 15% of my observations from good to bad and from bad to good, respectively. Just randomly switched. So which is how I know that the Bayes error rate, so the which is the absolute best possible error rate of any model, is precisely 0.15, because I just constructed my model like this. Okay, and then I started fitting logistic regressions, polynomial logistic regressions, where as variables. So in the first logistic regression, I used the first of them is like this. It's just linear logistic regression. So log odds. So log of my probability p over 1 minus p is just like a0 plus b1 x1 plus b2 x2. So the second model is a0 plus b1 x1 plus b2 x2 plus quadratic terms. So I don't know, maybe let me use c1 x1 squared plus c2 x2 squared plus c3 x1 x2. This is the model of degree 2. So then the model of degree 3 includes linear terms, quadratic terms, and terms of degree 3, right? So there's going to be 4 of them of degree 3. So the model of degree 4 includes those and terms of degree 4, and there's going to be 5 of them, right? So x1 to the 4, x1 cube, x2, and so on up to x2 to the 4. And so every next model is going to include more and more terms, but not just one extra term, but like every next is going to include k more terms than the previous model. And here is what I got. For a linear model, the decision boundary is going to be linear, and this is what you see here. So this is the true decision, the decision boundary. And of course, a linear decision boundary is a pretty poor fit for my inverse tangent curve, right? Because my inverse tangent curve, it has an inflection point here. So no matter how you try to fit, a linear line into this, you're not going to, it's not going to really follow it very closely because of this inflection point. So which is why the test error is 0.2. It's probably not very impressive. Now, how about a quadratic model? So model of degree 2. So if you think about it, so quadratic curves, so they could be parabola, ellipses, hyperbola, but none of them has an inflection point, right? So which is why quadratic models are not a very good fit either. So which is why what you see here, the quadratic model, the decision boundary is slightly different, right? Is now curved, and it's probably a piece of a parabola or a hyperbola or a very huge ellipse, I don't know. But it still is not a very good fit because, a quadratic curve cannot have inflection points. But starting from degree 3 and onwards, the fit is 0.17, which is kind of decent. And you see that curves of degree 3 and higher, they already can have an inflection point, which is why it is possible to design a curve of degree 3 or higher that kind of resembles this inverse tangent quite closely. And this is why the error becomes improved, right? So it becomes smaller. Now, when degree is too high, 6, the error starts going up because it just, the decision boundary of our model is just too wiggly, and it starts fitting random noise rather than the true date. So in particular here, you see this observation is on, no, stop, this is okay, but this is, this observation is on the right side, but there are kind of a number of observations, unusually a large number of observations here that are on the wrong side, and they are probably pulling it a little bit higher up here. So which is why it's more wiggly. So now what I did, I compared the training test and 10-fold cross-validation errors for this polynomial logistic regression of various degrees. So from degrees from 1 to 10. So notice that 10-fold cross-validation and test errors are pretty close. So which tells us that the 10-fold cross-validation does a very good job in this case. So another difference from what we saw in regression problems is that, so notice that the curve, the error rate, even for the training error, does not go down all the way. So the general trend is down, yes, but it does not go down all the way. So in particular, it goes up here and then goes down. It goes up here and then goes down. So this is explained by the two facts. So one fact is that in order to fit the model, so when we fit a logistic regression, we choose a logistic regression with the lowest cross entropy, right? So we do not choose a logistic regression that minimize the error rate. So we choose parameter models that minimize the cross entropy, which is kind of a similar thing, but it's not exactly the same thing, right? So which is why it may not go down all the way. So the other thing is that when we fit a logistic regression, we do it by gradient descent, right? So whereas when we fit a linear regression, we just do it by directly solving the equations, right? So for a linear regression, we just have a closed form solution. But for a logistic regression, we do a gradient descent. And in particular, when we have too many predictors, and notice that the number of predictors here just goes up quadratically. So the number of predictors for a two-variable polynomial logistic regression of degree 10 is not 10. It's going to be 1 plus 2 plus 3 plus on and so on plus 11, right? So the number of predictors here is actually plus 11, which is what, 12 choose 2. So it's 66. No, not 66. In any case, so you can compute it, right? So this is 12 times 5.5, right? Yeah, I think it's correct. So my point being is that when there are just too many predictors for a logistic regression, then the gradient descent may not work very nicely and may kind of stuck. And when that happens in R, so it still produces the estimates, the model, but it prints a warning. So when I did this experiment, I saw these warnings. So which tells us that that there are just too many estimates. So if there are too many predictors for a linear regression, then it just wouldn't work. So if the number of predictors is more than the number of observations, then a linear regression just wouldn't work. Logistic regression would still kind of try to work, but it would report a warning. So, and even if the number of predictors is not bigger than the number of variables, but still considerably large, then it may happen that gradient descent runs into some troubles when it just every next step of gradient descent does not improve much further, and because of that, it stops and produces a warning message. So this is probably what happened here. So this is why the training error for a logistic regression does not have to go all the way down. So sometimes it goes up, sometimes it goes down, but of course the general trend is still going to be down, but it's not monotonic. All right, so here is a little quiz for you.